This is part 6 of a series on CNN. In this video, we will look at the Convolutional LSTM. Convolutional LSTM is a type of neural network that combines the convolutional neural network and the long short-term memory model. It is designed to learn from videos, i.e. image sequences, which are spatiotemporal data that contain both spatial and temporal dependencies. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In the final chapter of the CNN series, we will look at the Convolutional LSTM. We will look at the basic architecture of the ConvLSTM and implement a custom class for it. And let's look at the moving MNIST dataset that will be used to test this model. Finally, we will use many-to-one and many-to-many models to predict the next sequence of images in the moving MNIST dataset. The Convolutional LSTM was first introduced by Xingjian Shi et al. In their 2015 paper titled Convolutional LSTM Network, a machine learning approach for precipitation nowcasting. In this paper, they proposed a novel convolutional LSTM network for precipitation nowcasting. They formulated precipitation nowcasting as a spatiotemporal sequence forecasting problem that can be solved under the general sequence-to-sequence learning framework. The goal of precipitation nowcasting is to use the previously observed radar echo sequence to forecast a fixed length of the future radar maps in a local region. In this paper, they showed that this model outperformed conventional LSTM and state-of-the-art computational algorithm ROVER for precipitation nowcasting. The structure of the convolutional LSTM is almost the same as that of LSTM with p-pole connections. The only difference is that in these networks, convolutional layers are used instead of dense layers to receive the current input image xt and the previous hidden state h, t-1. We took a closer look at the p-pole LSTM architecture in this video from our previous recurrent neural network series. This can be represented by mathematical expressions as follows. The convolution operations are performed between the input image xt and wf and between the hidden states ht-1 and rf. This symbol represents the convolution operation. Wf and rf correspond to the filters of the convolutional layer. An element-wise product is performed between the cell state ct-1 and the p-pole connection pf. This is the output of the forget gate. Similarly, in other gates, the convolution operations are performed as well. These formulas are given in equation 3 of the paper. The input data is a sequence of images as follows. The 2D image is changing over time. The image at each time step is fed into the convolutional layers, and the features of the image are extracted. The LSTM part learns how these features change over time. Once training is complete, we can use this model to predict the next image. Next, let's implement a Python class for the 2D convolutional LSTM model we looked at on the previous page. The class for the p-pole LSTM model used in this video is as follows. The 2D convolutional LSTM model is very similar to this. In the p-pole LSTM model, dense layers are used for wf and rf like this. In the 2D convolutional LSTM model, 2D convolutional layers are used for WF and RF instead of dense layers. For p-pole connections, we use TensorFlow's variables. This is to perform element-wise multiplication of these variables and the cell state C. The LSTM cell function computes the outputs of each gate according to the formulas shown on the previous page. When an input image X is fed into the 2D convolutional layer WF, the feature map of X is output. Similarly, when the hidden state H is fed into the 2D convolutional layer RF, the feature map of H is output. The cell state C is multiplied by the p-pole connections. Applying the sigmoid function to the result of adding all of these together gives us the output of the forget gate. In this way, the outputs of other gates are computed. Finally, the hidden state H and the cell state C are returned. Next, let's write the call method. This function takes the multiple sequences of images X as an input. H and C are initialized to 0 since there is no previous time step. Now to find H and C for each time step, we repeat the following procedure for a given number of time steps. The second dimension of the input image is the number of time steps. We use the LSTM cell function written above to get H and C. H and C become the inputs for the next time step. At the end of the iteration, the final H is returned to be passed to the output layer. Next, let's look at the moving MNIST dataset that we will use to evaluate the convolutional LSTM model. The moving MNIST dataset was introduced by Nitish Srivastava et al. In their 2015 paper, Unsupervised Learning of Video Representations Using LSTMs. Moving MNIST contains 10,000 sequences, each of length 20, showing 2 digits moving in a 64 by 64 frame. We will use a convolutional LSTM model to learn the sequences of these images and predict the next sequence of images. Next, let's preprocess the moving MNIST dataset and visually observe a sequence of images. Load the moving MNIST dataset. This dataset is available for download from this site. Each image is a 64 by 64 matrix. The length of the sequence is 20. And the number of image sequences is 1 to 1,000. We swap the first and second dimensions. An example of an image sequence is as follows. The 2 digits move over 20 periods within a 64 by 64 frame. We will only use 5,000 sequences because it takes a long time to train a model. And we normalize the pixel values of each image to values between 0 and 1. To use 2D convolutional layers, we add a channel dimension at the end. Since this is a grayscale image, it only has one channel. Split the dataset into training data and test data. We use 90% of the dataset for training and 10% for testing. Next, we generate the input and output data for the model. Image frames 1 to 19 are used as input data, and 2 to 20 are used as output data. This is for a many-to-many model of LSTM. Visualize a sequence of images. The results are as follows. Finally, we save the preprocessed training and test data for later use. Let's run this code. We got the following results. Now let's build a convolutional LSTM model. First, let's create a many-to-one model. As we saw in the LSTM tutorial, a sequence of images from 1 to 19 is input to the model, and the 20th image is output. The recurrent layer consists of a 2D convolutional LSTM model, and the output layer consists of a 2D convolutional layer. The loss is computed using the predicted y-hat and the ground truth y. Binary cross-entropy can be used as the loss. Actually, this is a regression model. So we can also use the mean squared error as our loss. However, for image data, all pixels are normalized to values between 0 and 1, so cross-entropy can be used for regression problem. According to section 4.1, the authors of the paper also used cross-entropy loss. This is the many-to-one convolutional LSTM model. Now let's implement this model in code. We'll use the custom 2D convolutional LSTM class we built earlier. Load the pre-processed moving MNIST dataset. This data is for a many-to-many model. Since we are going to build a many-to-one model, we will only use the last image in ytrain and ytest. Build a many-to-one convolutional LSTM model. Create an input layer. The input layer receives 5-dimensional data like this. The input data xtrain consists of sequences of 19 images. Add a 2D convolutional LSTM layer. And add a batch normalization layer and a RealU activation layer. Finally, we construct the output layer using a 2D convolutional layer. The output layer outputs a single image. Create and compile this model. As mentioned in the previous page, we use the binary cross-entropy loss. Fit this model to the training data. The batch size is set to 50, and the number of iterations is set to 100. Once training is complete, we save the weights of this model so that they can be used in our prediction model. Let's check the loss history. During training, the training error and the test error are reduced like this. The final output of this model has the same dimensions as ytrain, 64 by 64 by 1. Next, let's use this model to predict a sequence of images. Create the same model we used in the previous page and load the weights of the trained model. Select one sequence of images from the test data. And we make this a 5-dimensional array and feed it into the model. When we feed this data into the model outputs the next predicted image. Save the predicted image to the p-result list. Then we append the predicted image to the existing X sample and predict the next image with the sequence of the last 19 images. In this way, we predict the next sequence of 5 images. Plot the ground truth image and a sequence of 5 predicted images. The prediction results are output as follows. The first image is the ground truth image, ytest. And the next 5 are a sequence of the predicted images. The first predicted image is somewhat accurate. But from the second time onwards, the image becomes increasingly blurry. This is because the predicted image is fed back into the model to predict the next image. For more accurate predictions, we need to use more training data, build a deeper model, and increase the number of iterations. We only used 5,000 out of 10,000 sequences. Let's run this code. We got the following results. Next, let's build a many-to-many model. As we saw in the LSTM tutorial, each recurrent time step outputs a predicted image through the output layer. We use a time-distributed 2D convolutional layer as the output layer. Alternatively, we can use a 3D convolutional layer. At each time step, the loss is computed and backpropagation through time is performed. Next, let's implement a many-to-many 2D convolutional LSTM model in code. This time, we will use Keras' ConvLSTM 2D class. Load the pre-processed moving MNIST dataset. Since this is for a many-to-many model, we will just use it as is. Build a many-to-many convolutional LSTM model. The input layer receives 5-dimensional data like this. We can also specify the time step dimension as none. Add ConvLSTM 2D layer from Keras. Since this is a many-to-many model, set the return sequences argument to true. And the output layer uses a time-distributed 2D convolutional layer. Instead of using time-distributed 2D convolutional layer, we can use a 3D convolutional layer in the output layer as follows. The many-to-many model takes 5-dimensional data as input and outputs 5-dimensional data. This is because the predicted image is output at each time step. The loss was reduced like this in both cases, where a time-distributed 2D convolutional layer was used and a 3D convolutional layer was used in the output layer. Next, let's use this model to predict a sequence of images. Load training data and test data, and load the trained model. The code to predict the next image is identical to the code used for the many-to-one model. The only difference is that we only use the last image from the outputs of this model. The prediction results when using a time-distributed 2D convolutional layer in the output layer are as follows. And the prediction results when using the 3D convolutional layer are as follows. Both results are similar. Let's run this code. We got the following results. So far, we have looked at the convolutional neural networks through 6 videos.